Now, in this session, we are looking at methods of preparation of alkyl halides, actually of hydrocarbons. I told you alkyl halides are not the only hydrocarbons we have. We also have aryl halides. So here I'm going to be a bit more elaborate about method of preparation. The first method I will see is how we can get hydrocarbons from alkenes. How do I get hydrocarbons from alkenes? If I have an alkane, I can convert that alkane to a chloroalkane, which we call chlorination. Some books use what we call chlorine and UV light. In case you're using that synthesis, make sure you use limited chlorine. In case you use an excess of chlorine, you should specify that you're using limited chlorine. For example, if I want to convert ethane to chloroethane, CH3CH2Cl, I'll use limited chlorine in presence of UV light. The moment you don't limit the chlorine, you're likely to get very many products. You'll get very many substituted products, which are actually, you can get CH3, CH, Cl2, you can also get CH3C, Cl3. So to avoid getting all these tri-substituted products and the disubstituted products, use limited chlorine. That's one way of synthesis from alkenes. However, if you don't want a mixture of products, and to be more specific, you can convert the ethane to chloroethane using what we call sulfuryl chloride in the presence of a catalyst called dibenzoyl peroxide. Di-benzoyl, then peroxide. That reaction is done at a temperature of 40 to 80 degrees Celsius. It will give you chloroethane. It will give you chloroethane. I want to see an example in which this synthesis can be applied, and I'm thinking about it. Actually, even if I elongate this chain and I use propane, CH3, CH2, CH2, CH3, that's propane, I can convert it to chloropropane using the same reagent. Sulfuryl chloride, dibenzoyl peroxide at a temperature of 40 to 80 degrees Celsius. This is not a new reaction to us. We looked at it when we are looking at alkenes. Now, which synthesis am I thinking about? I'm thinking of a synthesis in which we want to convert. I'm looking at a synthesis in which we shall convert propane. Somebody is saying convert propane to hexane 1-ol. How do you convert propane to hexane 1-ol? How will you do that synthesis? This is propane, which is 3 carbon atoms. You want to convert it to hexane 1-ol. Hexane 1-ol has 6 carbon atoms. These are 4, 5. Then you have a CH2OH. That is hexane 1-ol. So in this kind of reaction, I expect you to use what we call Wurtz synthesis somewhere. How will you do that? I expect you first of all to chlorinate the propane, probably using the sulfuryl chloride and then dibenzoyl peroxide at a temperature of 40 to 80 degrees Celsius. This will give you CH3, CH2, CH2, Cl. Then you can use the wood synthesis using sodium and dry ether. Don't heat. This reaction does not require heating. It will give you CH3, CH24, CH3. Those are 6 carbon atoms. And then you still have to do the same reaction. Sulfuryl chloride, dibenzoyl peroxide. The dibenzoyl peroxide uses a temperature of 40 to 80 degrees Celsius. That will give you CH3, CH24, CH2Cl. Then here, you can do your last step using sodium hydroxide. It should be aqueous. Specify it as aqueous, then heat. If you're to get the marks, we shall give you a mark for that, a mark for that. This reagent, get that, give you a mark for that. Reagents here, get that mark, get that, and that. So that's one synthesis in which you can apply the reaction I've just talked about. That's one reaction by which we can get haloalkanes from alkenes themselves. I hope Linda and Marvin have got this. Let me look at another synthetic route by which we can get hydrocarbons. We can get them from what we call alkenes. So how can I get hydrocarbons from alkenes? Well, first of all, look at chlorination of the alkenes. The first reaction is that chlorine reacts with alkenes in the presence of carbon tetrachloride, an inert solvent, presence of tetrachloromethane, to form what we call vicinodihalides. Can I look at an example? Why not? So if I have an alkene like propene, propene is an alkene. I react it with chlorine in the presence of carbon tetrachloride. We saw this reaction when we are looking at alkenes. I'll form this product here, CHCl, CH2Cl. This is what we call a vicinodihalide called 1,2-dichloropropane. This reaction does not require you to heat. So in this reaction, we are converting an alkene to a vicinodihalide. That's a very good reaction by which we can convert alkenes. This reaction can also be done using bromine. In case I use bromine, for example, I have this alkene here. This alkene here has a name that I want some of you to think about. Which name do we give that alkene? I know Kezia is thinking about it. This alkene is called phenylethene. If I want to convert phenylethene to a vicinodihalide, I can choose to use bromine in presence of carbon tetrachloride. I'll have this product of mine here. This product has a bromine atom here and another bromine atom on that carbon. Which name do we give that dihalide? Think about it, but it's also a vicinodihalide. I know you're thinking of the same name I'm thinking about, which is 1,2-dibromo-2-phenyl That's the name of that vicinodihalide. 1,2-dibromo-2-phenyl. On the carbon atom 1, we have a bromine atom. The second carbon also have another bromine atom. So we call it 1,2-dibromo 2-phenyl. Ethane. Can also get hydrocarbons from what we call alkynes. You can get them from alkynes. And for alkynes, we can get both vicinal and germinal dihalides. Let me look at an example. If I have ethine can be converted to a hydrocarbon called 1,1,2,2 tetrahaloethane. The halo means it can be chloro, it can be bromo. Iodos are not so common for that reaction. This reaction takes place in the presence of a catalyst. That catalyst is called Kieselguhr catalyst, specifically for ethine. Kieselguhr shouldn't confuse you, can call it silicon 4 dioxide catalyst and iron filings. This reaction occurs at ordinary temperatures. I know you remember the mechanism for that reaction. Not this one. The next reaction we shall see. Remember the mechanism. So if I want to convert ethine to maybe CHCl2, that compound can be written as CHCl, then there is a halogen atom here, a chlorine atom here, CHCl, another chlorine atom there. We use chlorine. That chlorine is used in excess in the presence of silicon 4 oxide and then iron. The same reaction can be done using bromine. If you use bromine in presence of silicon 4 oxide and iron, you'll get 1,1,2,2 tetrabromoethane. This compound here is called 1,1,2,2 tetrabromoethane. So this reaction I've talked about is specific for ethine. For ethine, this catalyst is used and the halogen is used in excess. Now, if I want a germinal dihalide, you can prepare a germinal dihalide. I will say germinal dihalides can also be formed. By reacting alkynes with the hydrogen halides. In the presence of light or metal halide catalyst. The metal halide catalyst is used in case you're using a gaseous phase. Which metal halide catalyst do we commonly use? We use mercury 2 chloride or copper 1 chloride. This occurs in gaseous phase. Why am I saying gaseous phase? That's why the copper is dimerized. The copper and chloride is dimerized. Examples. If I want to convert ethine to a germinal dihalide in this case is 1,1-dichloroethane. That one there. This is in contrast to the previous reaction. This reaction requires me to use an excess of hydrogen chloride in the presence of copper 1 chloride catalyst in a gaseous phase. If I want maybe to convert ethine to a germinal dihalide, In this case, the geminal dihalide I want is that one. Then the chlorine atoms are on that carbon atom. It's called 2,2-dichloropropane. I'll use excess hydrogen chloride. Actually, I may also want to have bromine atoms. Let me not be static. In case I want bromine atoms there, I'll have to use bromine, excess hydrogen bromide, in the presence of copper 1 chloride. I can convert phenylethyne to geminal dihalide. In that case, I may choose to use excess hydrogen iodide in the presence of copper 1 chloride. The geminal dihalide I may get in this case is this dihalide here, which has iodine atoms at that carbon atom, and then a CH3. So that is in a case I want geminal dihalides. What have we looked at so far? We have so far looked at how to get hydrocarbons from alkenes. We have seen how to get hydrocarbons from alkenes. We have seen how to get hydrocarbons from alkynes, specifically beginning with ethyne. This is a specific reaction in which you use Kieselguhr catalyst. We have also seen how to get them from other alkynes. In case we want the geminal ones, the halogen atoms are on the same carbon atom. Now I want to see how can we get haloalkanes from alcohols. How can we get haloalkanes from alcohols? I'll begin with the chloroalkanes. The chloroalkanes can be formed by reacting alcohols. By reacting alcohols with phosphorus 5 chloride, that reagent there. For example, I have propan 1-ol. If I react propan 1-ol with the phosphorus 5 chloride, let me write the whole equation for the reaction. If I react this with phosphorus 5 chloride, of course the major product is 1-chloropropane. But in the same reaction, I have that product, POCl3 and then HCl. I'm completing this equation because sometimes you can be required to write the whole equation, the balanced one. Okay. All right. I can also have a secondary halalkane. For example, this one. I mean a secondary alcohol. If I use phosphorus pentachloride here, I get a similar reaction. I'll have CH3, CH, Cl, CH3, POCl3 plus HCl. That is a preparation of haloalkanes. In case I want to use an alcohol and I want to get chloroalkanes. And you realize that in both these reactions, there's formation of hydrogen chloride. This hydrogen chloride is a gas, and it is formed as dense white fumes. So if you ask the observation, you can say, somebody can say, state what is observed when ethanol, propan 1-ol, propan 2-ol is reacted with phosphorus pentachloride. You simply say dense white fumes. What are those dense white fumes? They are fumes of hydrogen chloride gas. Which other way can we use to form chloroalkanes? Chloroalkanes can also be formed from alcohols by reacting alcohols with another reagent that can substitute the phosphorus pentachloride. That reagent is called sulfur dichloride oxide. It is one name, sulfur dichloride oxide. Sulfur dichloride oxide is sometimes called thionyl chloride. Sulfur dichloride oxide is sometimes called thionyl chloride. This reaction is done in the presence of a small amount of pyridine. Presence of a small amount of pyridine. Pyridine is a benzene ring with a substituted nitrogen atom in it. You can go about that structure in case you want to know it. But in our synthesis, we don't usually draw that structure. For example, if I react ethanol with thionyl chloride, dear students, I don't want you to confuse thionyl chloride with sulfuryl chloride. Sulfuryl chloride is this reagent here. This reagent here is called sulfuryl chloride. So this is sulfuryl chloride. SO2Cl2 is sulfuryl chloride. But then So SOCl2 is what we call thionyl chloride. Now, when you come here and you want to use that reagent, thionyl chloride, some of you confuse it with sulfuryl chloride and instead write SO2Cl2. The other one is used in chlorination of alkenes. This one is used in formation of chloroalkanes from alcohols. This reagent requires you to use pyridine, a small amount of it, then you get the chloroalkane that you want. I can also have this kind of alcohol, a tertiary alcohol. So if I react this with thionyl chloride in presence of pyridine, I'll get CH3, 3CCl. If you want other products of this reaction, you'll have sulfur dioxide and hydrogen chloride. So in the same reaction, we shall also form dense white fumes. Not only that reaction leads to formation of chloroalkanes, we can similarly get chloroalkanes if we react alcohols. Chloroalkanes can also be prepared by reacting alcohols with saturated dry hydrogen chloride gas in the presence of anhydrous zinc chloride. We shall later see what we call Lucas reagent. So this reaction is also very okay. You can use ethanol, for example, here. You react the ethanol with dry hydrogen chloride gas in the presence of zinc chloride catalyst, anhydrous, and then you reflux. This reaction will give you chloroethane. But why do you go for it? Why do you rush for it? Yet you have very many other reactions by which that can be done. However, knowing it is not a problem. You can have propan 2-ol. Propan-2-ol refluxed with dry hydrogen chloride in presence of zinc chloride catalyst, and then you reflux will give you 2-chloropropane. For tertiary alcohols, that reaction can occur readily even in presence of water, and concentrated hydrochloric acid can be used. So in case I have a tertiary alcohol, this reaction will occur even with concentrated hydrochloric acid. Briefly, simply adding concentrated hydrochloric acid to tertiary alcohol, like this one here. You simply add conc hydrochloric acid, it will give you the conversion. And for it, the reaction occurs very fast. If I want to use a tertiary alcohol to form a bromoalkane, I can react the tertiary alcohol with sodium bromide in presence of concentrated sulfuric acid. That is also another unique reaction for the tertiary alcohols. Okay? For example, I have this tertiary alcohol, COH. If I react it with sodium bromide and concentrated sulfuric acid, it will give me CH3, and then CBr. In brief, this reaction is indirect reaction of the alcohol with the hydrogen bromide. But hydrogen bromide is usually prepared in situ by this reaction. The reaction between sodium bromide and conc sulfuric acid will give me sodium hydrogen sulfate and hydrogen bromide, which comes and reacts with this alcohol to form the bromoalkane. However, this reaction and the previous one do not occur easily for the primary alcohols and may require you to reflux. So if I want a bromoalkane from, if I want alkyl bromides, actually I can also get an alkyl bromide from the tertiary alcohol. I'd forgotten this reaction. If I react a tertiary alcohol with phosphorus tribromide, it will give me the same product. So these two reactions occur easily for the tertiary alcohols, very easily. But for the primary alcohols, like this one, ethanol, the reaction does not easily occur. And if you want that reaction to occur for primary alcohol, you must reflux. I want you to note that difference. This one requires you to reflux, so that you get CH3, CH2, Br. And in the same case, if you're using the first reagent, sodium bromide, conc sulfuric acid, and you want the reaction to occur to give you CH3, CH2, Br, still you must reflux. That's the only difference. That for tertiary alcohols, the reaction occurs spontaneously. It doesn't need you to reflux the mixture. For primary alcohols, you will have to reflux the mixture in case you want alkyl bromides. So far, I've seen how you can prepare alkyl bromides and alkyl chlorides. How about the alkyl iodides from alcohols? In case I want alkyl iodides from alcohols, I will add iodine to a mixture of an alcohol and red phosphorus and then reflux. What does the phosphorus do? I hadn't talked about this previously. The phosphorus, first of all, reacts with the iodine. on heating form the phosphorus triiodide. That's the same way the phosphorus tribromide is formed. You react red phosphorus with iodine and then reflux the mixture in a water bath. So the phosphorus triiodide or phosphorus tribromide formed now goes on to react with the primary alcohol. So the phosphorus triiodide here react with the primary alcohol to give me iodoethane. That reaction requires us to reflux on a water bath. Similarly, you can get alkyl iodides by reacting an alcohol, for example, the ethanol here. You react the ethanol with concentrated solution of hydroiodic acid. But that concentrated solution of hydroiodic acid is prepared in situ from a solution of conc phosphoric acid and the potassium iodide. Okay, it's prepared from a concentrated solution of phosphoric acid and potassium iodide. It's prepared in situ. This reaction here will occur this way. You have the potassium iodide reacting with phosphoric acid to give you hydrogen iodide, which we want, and potassium phosphate. The reaction is balanced by 3 here on the potassium iodide, and then what else? And a 3 here, balance the iodine. So this reaction mixture here is intended to prepare for us the what? The hydroiodic acid, the concentrated solution of hydroiodic acid, which now comes and reacts with the ethanol, form the alkenes. However, if that reaction disturbs you and you are in a synthesis, don't cry a lot. Use, first of all, get the ethene, and to the ethene add hydrogen iodide gas, which is dry. You get the product that you want. That's one trick you can use. Unless it is not a thin and it's another alkene, then you can try other methods. How can we prepare the same compounds from what we call carbonyl compounds? I also needed to see that. Although we haven't looked at carbonyl compounds, but we need to know how to prepare alkyl halides from, I'll begin from, we want them from aldehydes and ketones. So if you want aromatic and simple carbonyl compounds, we shall react carbonyl compounds with phosphorus pentachloride. Look at this reaction. I have ethanol. That compound is called ethanol. Sometimes it is written as CH3CHO. If I react this compound with the phosphorus pentachloride, phosphorus 5-chloride, this double bond here of the oxygen atom is substituted by 2 chlorine atoms. You get CH3C, Cl, Cl, CH. Or you can write this as CH3, CH, Cl2. That's the reaction that takes place. In case you want the other product, it is POCl3. 3 chlorine atoms plus these 2 that makes up the 5 that we are here. So that is one way by which you can get haloalkanes from aldehydes and ketones. And in this case, you get the germinal ones, in which the carbon atoms are on the same, in which the halogen atoms are on the same carbon atom. I can have another example. If you have a ketone like propanol, which you sometimes write like this, react the ketone with phosphorus pentachloride. you will get a geminal dihalide still. The chlorine atoms are both on the same carbon atom. I can have benzene carbaldehyde or benzaldehyde, which we write like this. Or you can simply write it. I think you can draw a better ring than mine. You can write it like this. If you react this with phosphorus pentachloride, you'll get this kind of compound, CCl, ClH. And if you want, you can go ahead, convert it to a diol by using sodium hydroxide solution and heat. Sodium hydroxide aqueous, heat will give you that compound. So that's one way by which you can pair alkyl halides from or aryl halides from aldehydes and the ketones. You can simply use phosphorus pentabromide in case you want bromine atoms here. That is also very okay. How about if I want aryl halides? I haven't so far looked at them. How do we synthesize aryl halides? I'll begin with the direct halogenation of benzene. You have looked at that reaction. That's one way by which you can prepare aryl halides. What are aryl halides? They are those ones in which the halogen atom is directly attached to the benzene ring. The halogen atoms are directly attached to the benzene ring. So if we do the direct halogenation of benzene, we can get the aryl halides. For example, if I use chlorine in presence of aluminum chloride, you know the product here is chlorobenzene. If I use bromine in the presence of maybe iron 3 bromide or aluminum bromide, I'll get bromobenzene. So by that I can prepare an aryl halide. The other way I can get aryl halides is by the reaction of the benzene diazonium chloride salt. I think I also looked at that when I was looking at benzene. So if I have the benzene diazonium chloride, it is this compound here. I have a negative charge and a positive charge there. And I want to convert it to chlorobenzene. If I want chlorobenzene from benzene diazonium chloride, this is called benzene diazonium chloride. Benzene diazonium salt or benzene diazonium chloride. If I want to convert it to chloroethane, I use copper 2 chloride catalyst. Copper 1 chloride actually. I use copper 1 chloride catalyst in presence of concentrated hydrochloric acid and then warm. If I want bromobenzene from it, I will use copper 1 bromide catalyst in presence of concentrated hydrogen chloride and then warm. In case I want to convert it to iodobenzene, That one is very simple. I simply use potassium iodide, but it must be aqueous, and then warm. So the benzene diazonium chloride is a very good tool for synthesis. It's a very good compound for synthesis because it can yield all aryl halides that we know that are synthesizable: chlorobenzene, bromobenzene, and iodobenzene. So I've looked at the way we can synthesize alkyl halides and aryl halides from different compounds. I hope that can boost your synthesis or your synthetic knowledge. It can boost your knowledge on synthesis. This is where I wish to stop. For the next sessions, I'll be introducing you to the chemical properties of hydrocarbons, which include what we call nucleophilic substitution reactions. Those are common reactions that they undergo, and they include nucleophilic substitution by molecular and the nucleophilic substitution unimolecular reaction. Have a good day. God bless you.